Number 8. The diagram below shows a penny smearing machine. An operator turns the big crank, this is the big crank, while feeding a penny into the space where the smearing wheel meets the smearing plate. That's this space right here. So this is the smearing wheel, this is the smearing plate, this is where the penny goes in and it gets smeared and pushed that way by the smearing force. The big crank turns sprocket A, this is sprocket A, which in turn turns sprocket B, this is sprocket B via the chain. This would ordinarily have little teeth in the sprocket. They're not shown here. This is just shown as a simple circle. Same thing here. There would be teeth on this sprocket that would intermesh with this chain. There's more information listed in the table. What was left off of this table was the 40 Newton force. That is the force applied tangentially to the big crank. So it's applied at a right angle to the big crank, 40 newtons of force. In class, I told you to use 80 newtons of force, but last year we used 40 newtons of force, and the solutions I'm going to show you use 40 newtons of force. Number 8 asks, the smearing wheel applies a force to the penny that pushes it to the right. What is the magnitude of this rightward force? In order to figure that out, we have to figure out how much torque is on this and the length of this lever arm, which is just the radius. And to get the torque on this sprocket and this smearing plate, we're going to have to figure out how much force is applied by the chain. To figure out how much force is applied by the chain, we have to figure out the amount of torque on this sprocket, which comes from the applied force applied to the big crank. So the first step is to figure out how much torque is given to this assembly right here. The big crank plus the sprocket, they have the same amount of torque. It's one unit moving together, so torque anywhere along this radius is the same. Torque equals force times radius, and as you go out farther in this radius, a larger radius means the force is smaller. As you move in closer, you get a smaller radius and larger force. My first step was to find the torque applied by the big crank. Torque equals force times radius. The force is 40 newtons. The radius is 0.3 meters. That was provided right here. That's the big crank length. So 0.3 meters. 40 times 0.3 gives 12 meter newtons, or newton meters, depending on how you like to say it. It says this same torque is applied to sprocket A, so the torque on sprocket A is 12 meter newtons. So that's just saying the torque on this is the same as the torque on that, because they're all moving as one body, and that's just the case when things are all fastened together. The torque is the same throughout. Now the next thing I did, I said torque equals Fr. It's the same formula as before, and now I'm saying that the torque is 12, because we just calculated that the torque was 12. But what I'm finding here is, what is the force with that torque if the radius is only 0.02 meters? The reason I'm finding that out, that's the sprocket radius. That's the radius of this little tiny circle here. So if we know the torque on this whole thing is 12, that means the torque on this part of it is 12. And that means if you have a little tiny radius this big, 0.02, what do you have to multiply that by? What force do you have to multiply that by to get 12? And this is how I solve it. 12, that's the torque, equals the force times 0.02. To solve for the force, you divide both sides by 0.02. This side divided by 0.02. This side divided by 0.02. These cancel out, so you're left with just force on this side. And this side is 12 divided by 0.02, which gives you 600. 600 newtons. So 600 newtons is the force that's applied to the chain, and which the chain transfers to sprocket B. So we just figured out there's a force right here where I'm making this dot, a 600 Newton force applied to the chain right there, and the chain transfers that force to right here. So it applies a 600 Newton force right where I made the dot. Now it's a little misleading the way I've drawn this diagram, because I've written 600 newtons out there. I should really draw it like this. 600 newtons. So that is going to create a torque. Here's the center of rotation. This is the force. This is the radius. We can figure out how much torque is applied to sprocket B. The torque on sprocket B is 600 newtons. That's the force of the chain, times 0.8 meters. 0.8 meters was the radius of sprocket B. And when we multiply that, we get 480 meter newtons, or newton meters. Now, again, I wrote, this torque is equal throughout sprocket B and the smearing wheel. So, what I mean by that is, this smearing wheel and this sprocket, they're connected together, they're fused, so the torque on the entire assembly is the same at any point. You could measure the torque at this radius, and the torque at this radius, and the torque at this radius, torque at that radius. Torque is the same everywhere. What's going to vary is, as the radius gets bigger, the force is going to get smaller. Now, we've got to we can use that knowledge to figure out what the force is at the smearing wheel. We know the torque. We know the torque is 480 meter newtons. Now, if we want to know the force right here, we need to know this radius, and that radius is 0.83 meters. So we just set up the torque that we calculated before equals some force times 0.83 meters, that's the radius. And solving for force, you get 578 newtons. Now, to solve for force, you want to isolate force, so we divide both sides by 0.83. This divided by 0.83 equals this divided by 0.83. When you divide this side by 0.83, you're left with force all alone. When you divide this side by 0.83, you get 578 newtons. So that's the answer to number 8.